In this example, we're going to cover Castigliano's theorem for beams. In this example, we have a simply supported beam with a uniformly distributed load across a grand total of 6 meters in length. Now we want to find the slope and deflection at B, and B is measured 2 meters from the left side of the beam. Now the problem has already given us that X needs to be measured from the left going to the right. So we're going to follow that just so that we make it easier on ourselves. Now the thing with Castigliano's theorem is before we begin, we need to apply P. And if we're going to start by finding the slope at B, then we need to apply a rotation of value P at B. Next, we need to go through and solve for our reactions. We've got AY and we've got CY. Now, since they've already told us that we're going to be taking X measured from the left, we don't actually need CY because he's never going to be on our little free body diagram. So we can go ahead and sum the moments about C and set it equal to 0, taking counterclockwise to be positive, so that we can find AY. So AY is going to be going opposite our nice direction, so negative AY times his distance of 6 meters. Then we have our 20 kilonewton per meter load going positively. So we have plus the base of 6, the height of 20, and the distance from his center, which is half of 6 over to C. Then we have P. P is just straight up going in the wrong direction, so minus P. Then what we need to do is solve for AY. So we're going to get that AY is equal to 60. This guy is actually 360. Then we're going to divide by 6. We have 60 minus P over 6. All that is going up. So now we need to make a cut. We're going to have to make 2 cuts. We have 1 cut before the applied P load, and we have a second cut after the applied P load, or moment, I should say. So let's analyze it section by section. So for section 1, we're going from 0 to X, and the maximum distance for X is 2 meters. So we need to draw our little free body diagram here. So we have AY, and we said AY was 60 minus P over 6. This distance is X. Don't forget that we have our distributed load here, and that's 20 kilonewtons per meter. Then we're going to have internal shears and normals and moments. So what we're going to do is sum the moments about the cut and set it equal to 0, taking counterclockwise to be positive. So what we're going to find is we have M going in our positive direction. That's good. Then we're going to work on our AY load there. So he's going to be negative. That's negative 60 minus P over 6 times his distance of X. Then we've also got a positive, because our 20 kilonewton load is going to be going positively. Positive the base of X times the height of 20 times the distance of 1/2 X. So M is going to equal 60x minus P over 6x minus 10x squared. So del M, del P, the partial derivative of M with respect to P, is the only guy who has a P term is him. So that's going to be minus 1/6 times X. And if we set p equal to 0, we're going to get our actual moment equation being equal to 60x minus 10x squared. Maybe we shouldn't write it in that color. We'll put it in blue. So m is equal to 60x minus 10x squared. So del m del p, and there is our m equation as well. Next, we're going to move on and do section 2. Section 2 goes from not 0, he starts at 2 meters and goes all the way to 6 meters. So we need to draw our free body diagram. Remember that we have our distributed load up here, same thing as before, 20 kilonewtons per meter, but don't forget that we also have point moment of P, and he was a distance of 2 meters. Now the overall x here at the bottom, and we also have AY being still 60 minus P over 6. Lastly, we have our internal shears, normals, and moments. And that's our free body diagram for section 2. So we're going to sum the moments about the cut, set it equal to 0, taking counterclockwise to be positive as per my usual. We have m, and we have, starting with AY, minus 60 minus P over 6 times his distance x, plus we have the base of x times the height of 20 times half of that base of x, and then we have P. P is going the wrong way. So our m equation for this is going to be P minus 10x squared plus 60x minus P over 6 times x. So we've actually got 2 P terms this time. So del m del P, that partial derivative of m with respect to P, we're going to have 1 minus 1 over 6 times x. Actually, not too terrible. And if we set P is equal to 0, we're going to get m is equal to 60x minus 10x squared. And if you notice, that is the same. This guy is the exact same. And you might be thinking, wow, that's kind of weird. Well, you're going to find out that it makes perfect sense because remember that P is fake. So if P doesn't exist, then this beam's loading situation doesn't change at all. So actually it does make perfect sense. So when you remove P, it's the same situation. So that's logical. Next, what we need to do is find the slope at B. And I'm just going to take EI out of the equation just for now so we can talk about the integrals. So EI times the slope at B is equal to the integral for each of these sections. So for section 1, we went from 0 to 2. And we're doing del m del P. So del m del P was minus 1 over 6 times x times our moment equation, which we said was the same one. So 60x minus 10x squared dx. Plus, can't forget about section 2. Section 2 is going to go from 2 to 6. So del m del P, 1 minus 1 over 6 times x. And our m equation, 60x minus 10x squared dx. When you solve this integral, we're going to get theta b is equal to 86.667. This is kilonewtons meters squared, and that would be over EI, but we have a value for E and we have a value for I. So for E, we have 200 gigapascals, and I, we have 150 times 10 to the 6 millimeters to the 4th. But we're writing our units because we have to be very consistent with our units. So we have 200 gigapascals. Giga is times 10 to the 9th. A pascal is a newton per meter squared. Then we have I, we said was 150 times 10 to the 6 millimeters to the 4th. So our units are all over the place. We've got newtons and kilonewtons, we've got meters and millimeters. So let's try to get rid of some. So we know that we have 1,000 newtons in 1 kilonewton. And that's going to go ahead. And kilonewtons are going to cancel here. Newtons are going to cancel there. That's wonderful. Then we've got millimeters and meters. Millimeters are on the bottom. So we have 1,000 millimeters per every 1 meter. And this we need 4 times. All right, so that's going to cancel millimeters and millimeters, and that's actually going to be meters to the 4th and meters down there. And you're unitless, which is exactly what we want because the slope at B is measured in radians, and this is going to be 2.89 times 10 to the negative 3rd radians. Bam, there we go. So really not too terrible. So we found slope at B. However, we don't want to just stop there. We want deflection at B, so we got to do the whole thing all over again, starting from scratch, but this time instead of a moment here for P, we're going to do a load. So a point load. So this time we're going to do a point load of P. Same thing, we're going to start the whole thing all over again. So we've got AY and we've got CY. Again, we're measuring X as they told us from the left to the right. So nobody actually cares at all about CY. Sorry, bud. So let's start by summing the moments about C and set it equal to 0 so that we can find AY. So we're going to have negative AY times 6. Then we've got plus P times 4. And also plus the base of 6 times the height of 20 times the distance, 1/2 of 6. So we're going to find that AY is equal to 60 plus 2/3 of P going up. Now this makes sense, right? Because P is closer to A than E is to C. And we still have that distributed load we gotta divvy out. So same thing, we're gonna make a cut before the point load of P and after the point load of P. So for section 1, we're going to go from 0 to X to 2 meters. We need to draw us a new little free body diagram here. So we have AY, who we said was 60 plus 2/3 of P. Our distance here is X. We have our distributed load. And we are before P, so he's not on here. So this is 20 kilonewtons per meter. Then we've also got shears, normals, and moments. All right, so if we sum the moments about the cut and set it equal to 0, taking counterclockwise to be positive as the usual, we're going to have M for the moment. Then we have our AY, who's going to be negative 60 plus 2/3 of P times his distance of X, plus we have the base, X, times the height, 20 times the distance from his center over to the cut, which is 1/2 of X. So we're going to find that M is equal to 60x plus 2/3 of P times X minus 10x squared. So del M, del P, you got one P term right there. So we're going to get 2/3 of X for del M del P. If we set P equal to 0 and solve for M, we're going to get 60x minus 10x squared. It is the same because the actual given system's loading never changed. So, shocker, that one is the exact same as it was before. For section 2, we're going from 2 meters to X to 6 meters. So we got to draw a new little free body diagram here. Overall distance, we have X. We have our given load. Then we actually did pass P. So P, given load was 20 kilonewtons per meter there. The distance over 2P was 2 meters. And we've also got AY. AY was 60 plus 2/3 of P. And then we have our internal shears, normals, and moments. So that's our little free body diagram for the second cut. So if we sum the moments about the cut and set it equal to 0, taking counterclockwise to be positive, we're going to get M for the moment. Then we have our AY, so he's going to be minus 60 plus 2/3 of P times his distance of X, plus we have the base, which is X, the height, which is 20, times the distance of 1/2 X, plus we have P. Now P is not times X, he's times X minus 2 meters, because he was already in a certain distance. So our moment equation becomes 60x plus 2/3 of P times X minus 10x squared minus P times X plus 2P. Woohoo, we have 1, 2, 3. 3 P terms. So this time when we find del M, del P, we're going to get 2/3 X minus X plus 2, which we're going to shorten that down a little bit. 1 minus 2/3, or the other way around, negative 1/3 X plus 2. Oh boy. And if you set P equal to 0, you get, shocker, the same thing that we have the entire time, 60x minus 10x squared. Again, the loading for the given system never changed. So this makes perfect sense. If there is ever a time you do not get that same value in this kind of problem, you probably did something wrong. So now if we want to find the deflection, the deflection at B, again this is times EI, this is going to equal the integral for cut number 1, so from 0 to 2, del M del P, which was 2/3 of x, times M, which same M, 60x minus 10x squared dx, plus the integral, this time for cut 2, 2 to 6 meters, del M del P, which was minus 1/3 times x plus 2 times M, 60x minus 10x squared dx. So not quite as fun to solve for, but still not bad. So you're going to get the deflection at B is equal to 293.33, again this is kilonewtons, times meters cubed over EI. But remember, we know E, we know I. E was 200 gigapascals, so times 10 to the 9th. Pascals are newtons per meter squared. I was 150 times 10 to the 6th millimeters to the 4th. So we got to clean up some units again. So we've got 1000 newtons per kilonewton, and that's going to cancel kilonewtons. That's going to cancel newtons. Then we've got millimeters and meters. So we've got 1000 millimeters per 1 meter. We've got that 4 times. And the 4 times is going to cancel this millimeters to the 4th. And this is meters squared and meters cubed. That's going to be meters to the 5th. So that's going to cancel this down to just meters. So we're going to get the deflection at B is equal to 0.00978 meters. And that's kind of a ridiculous number, so let's talk about it something less ridiculous. 9.78 millimeters. And that's how you solve slope and deflection using Castigliano's theorem.